In this Chalk Talk, we're investigating how semiconductors can change the world. In a lot of ways, that is an overarching theme here on Chalk Talk. But in this case in particular, we're talking about how semiconductors can help save energy and support green global initiatives. But how exactly? By changing how we design industrial motor drive systems. Hi, I'm Amelia Dalton, host of Chalk Talk. Innovation in industrial motor drives could not only save billions of dollars, but could also lead to a global reduction of energy grid usage. In this episode of Chalk Talk, Bob Card and Hunter Freberg from onsemi and I discuss the benefits that variable frequency drive, semiconductor optimization, and power switch innovation can bring to industrial motor drive applications. We also examine how our choice of isolation solutions and power packages can make a big difference for these kinds of applications, and how onsemi's robust portfolio of intelligent power modules, current sensing solutions, and gate drivers are a game changer when it comes to industrial motor drive applications. And before we get started, don't forget to click that link. There you can find even more information about this topic from onsemi. Hi, Hunter. Thank you so much for joining me.
Hi, Amelia. Thanks for having me.
Sure thing. And hi, Bob. Thank you for joining me.
Oh, thank you, Amelia. Nice to meet you.
Nice to meet you too. Okay, so we're talking about industrial drives and pumps today. But before we delve into the solutions in this arena, what kind of markets and industries are we talking about here, Bob?
Well, it's a pretty wide and big market. It's a $63 billion market with a 4.9% CAGR or cumulative average growth rate out to 2030. And it reaches a lot of different industries, some of which include water and wastewater, oil and gas, chemicals, pulp and paper, power generation, and food and beverage, to name a few. The Department of Energy, in cooperation with the Lawrence Berkeley National Laboratories, came out with the 2020 MSMA, which is the Motor System Market Assessment, where for the United States, they divided up the industrial drives and pumps into a block diagram of 5 components. And the first component is the controller, or the variable frequency drive. And that inside has the AC to DC conversion, as well as a 3-phase motor drive inverter. And then next to the right, the second component is the electric motor. The third component is the transmission or gears. The fourth component is the driven equipment, being the pump or blower. And then finally, the fifth component is the distribution system.
Excellent. Okay, so Bob, can we take a closer look at that 3-phase motor drive?
Sure. The input is the 3-phase AC supply, and it comes into this controller, and we actually invert it to DC and then back to AC again. And you might ask, why would you do that? And the benefit is inside there, you've got an MCU followed by 3 half-bridge gate drivers, followed by 6 switches. We have a high side, low side switch for each motor winding. So there's 3 motor windings, the U, V, and W. And by doing this, you can vary the duty cycle and the frequency, effectively changing the motor speed and make it a lot more efficient than if you were just to run it from the 3-phase power supply directly to the motor and run it just at 1 speed. And the main takeaway from this slide is this inverter is just stuffed with semiconductors.
Okay, so Bob, can you explain the variable frequency drive a bit more?
I sure can. On the bottom left-hand side of the screen, you can see I've got this reservoir of blue liquid and a 1-speed pump that's pumping that liquid into the reservoir. And then on the right of the reservoir, there's some sort of output. In the middle, there's a float. It's your classic float. And basically, that float is connected to a switch that's fed back to the pump. And if the reservoir gets too low, the pump turns on. If the reservoir gets too high, the pump turns off. It works great for many, many years. This is how pumps work for the most part. They do a good job, whether or not the load is constant or dynamic. The trouble is, it's just not a very efficient way of running a motor. A motor would prefer to be running all the time. At the bottom right, I've got a block diagram of a variable frequency drive where now the pump changes the frequency depending on the level of the blue liquid in this case. We have a flow position sensor now sitting on a metal rod, and it can tell the pump if that flow position is moving up and down a little bit, it'll increase the frequency or decrease the frequency. And so now with a VFD, you don't have this on-off situation. The motor is always running, just changing frequencies. The takeaway there is it's a lot more efficient than constantly turning the motor on and off.
Okay, so Bob, what kind of system savings are we looking at with this kind of motor drive system?
Well, one of the most interesting aspects of this 2020 MSA by the Department of Energy is the fact that they capture three potential annual savings opportunities if you do certain things. But before I get to that, one of the things that they first speak to is the fact that the annual consumption of the industrial pumps and drives in the United States amounts to 14.7% of the total US electrical grid load, which is not nothing. That's a huge amount, and I thought a striking number. But if you look at the first annual savings opportunity in green in their 5-component block diagram, you'll see that you can save potentially just in the controller where the VFD is, up to 45,000 gigawatt hours a year, $3.8 billion at 32.2 million metric tons of CO2 emissions. The next savings is with the electric motor, which has an annual savings opportunity of 15.5 thousand gigawatt hours, $1.3 billion, or 11 million metric tons of CO2 emissions. And finally, the third potential savings, according to the 2020 MSA, is with the distribution system. And that's 24,000 gigawatt hours, $2 billion, and 17.1 million metric tons of CO2. Basically, what's inside that controller, or the VFD, is a bunch of semiconductors, namely silicon, IGBTs, and wide bandgap, which includes silicon carbide or gallium nitride switches. If you look at the motor, that's really improving the load matching as well as advanced motor technologies like permanent magnets or synchronous reluctance. And then finally, the third savings in the distribution system is periodic maintenance. If you crunch these numbers in an Excel spreadsheet, you can see that the controller amounts to an 8.31% savings in annual consumption. The electric motor is 2.85%, and the distribution system is 4.41%. So the takeaway for me is with the VFD alone, that represents the largest annual savings opportunity of 45,000 gigawatt hours, $3.8 billion, and 32.3 million metric tons of CO2 just for semiconductors. And so for me, as someone involved in the semiconductor industry, that makes me feel good because I'm helping for sustainability and I'm helping for a greener earth. And more importantly, onsemi is a world leader in semiconductors, power semiconductors for this application, and therefore contributes greatly to sustainability and to a greener planet.
Fantastic. Now, can we also look at the power switch applications as well?
There's a very wide variety of sizes of these industrial pumps and drives. And these industrial pumps and drives benefit from different switches. And all of these switch technologies, we'll go through some of them individually with this plot. On the x-axis is the frequency or the switching speeds. The y-axis is power in watts. And so we'll first look at MOSFETs. The silicon MOSFET is really for low to mid power applications for these motors. They've pretty much reached their theoretical performance limit. The IGBTs, as you can see, they can go up to beyond a megawatt. They're scaled for high voltage and high power. It's an excellent bang for your buck for high wattage versus cost. But then you can see the silicon carbide actually switches faster beyond a megahertz and also up to 10 megawatts. It's a real breakthrough in technology. And one of the main reasons for that is the physics of silicon carbide exhibits excellent thermal performance with these high power applications. Finally, there's gallium nitride, which is another breakthrough technology. It's a lower voltage and high current, but much faster switching. It can go up to 100 megahertz. So when you look at all of these and you superimpose the industrial drives and pumps, you can see that it kind of overlaps on all four switch technologies.
All right. So, Bob, when it comes to motor drives, what kind of trends are you seeing?
The DOE with Lawrence Berkeley National Laboratories did the same report, the MSMA, back in 2002, so 18 years before this one. And you can see the trends for 1 to 5 horse. The trend is about 16% down, but 6 to 20 horse, it's flat. If you look at 21 to 50 horsepower, it's up 44%. 51 to 100 horsepower, it's up 97%. And then 201 to 500 horsepower, it's up 90%. And 501 to 1,000 horsepower is up 109%. So you can see a trend where you're getting, I think, the larger motors, which probably used to be more diesel or petroleum or gas, are now being powered by electric because of these added and improved efficiencies with semiconductors.
So, does this map to actual applications?
Oh, yes, it does very nicely. And so you've got these industrial pumps and drives that many applications. That includes conveyor belts of all different sizes and shapes for many different industries, fan control and blowers, pumps for liquid and gas, liquid agitation, and also centrifuge, separating particles and liquids, just to name a few. And the beauty of all of this, all of these applications, is they all use a very similar topology for electronics inside the inverter. And that includes the MCU, the half bridge gate drivers, and the high side and low side switches.
All right. So, Bob, can we dig a little deeper into the details of this three-phase inverter?
Sure, we can. On the far right, you can see in gray the motor itself, which has three windings, the U and the V and the W windings. And that motor can be sensorless or it can have sensors. In this case, I've got Hall sensors, but you could have inductive position sensors. And the Hall sensors, they register the magnetic field north when the rotor with the magnets are spinning. And that informs the controller in gray on the left where the rotor is in its spin. And the controller is running some sort of commutation sequence like trapezoidal, sinusoidal, or field oriented control. And at PWMs or duty cycles, these gate drivers, which are set for 20 volts, in this case for silicon carbide, and those gate drivers drive the high side, low side switches. You'll notice there's a high side, low side switch for the U, for the V, for the W, for a total of 6 switches. Now, I have 4 switches in parallel for each of those switches, so there's really 24 in here. And I'm just doing that to illustrate the fact that for really high power motors, you may want to put these switches in parallel, and that helps reduce the RDS on, which greatly reduces the conduction losses when you're spinning that motor. Now, each phase, you might want to have an eye sensing solution there, and I put in our NCS 2032 devices. And these are basically op amps with some fairly complicated feedback resistors. And by using an integrated solution like the NCS 2032, it's just an easier design, and you don't have to do all the difficult work trying to design around op amps because they're pretty finicky. We also have the NCP 718 LDOs that takes that 20 volt rail for the gate drivers and drops it down to 5 volts to power the Halls and 3.3 volts to power the processor. We also have the NCP 3064 flyback to deliver the 20 volt rail for the DC input. You know, when you do this PWMing of the switches, basically duty cycling has an averaging effect on the voltage going into the motor windings. And so by duty cycling it from, let's say, 25%, 50%, 75%, in effect, you're changing the average voltage going to the motor windings, and therefore you have really precise motor speed control that way. But you can also control the motor speed with the frequency coming out of the processor. And the motor torque is a function of the current delivered to the windings relative to the permanent magnet strength.
Fantastic. So, Bob, let's also talk about our gate drive options here.
Sure, it's half the story, right? You got the switches and you got the gate driver and then you have the MCU. So that MCU puts out an output voltage of, if you're lucky, 0 to 3.3 volts. You need to level shift that up to be able to turn on and off the silicon switches, the IGBTs, or the silicon carbide. But you need different gate drivers for different switches. In other words, for turning on silicon, you're going to need 0 to 10 volt swing. For turning on and off IGBTs, you need 0 to 15 volt swing. And for turning on silicon carbide, you need to go up to 18 volts. And depending on the silicon carbide switch, you also might need to go below 0 volts. For our second generation 3MS silicon carbide switches, you benefit from going down to -3 volts below ground, below 0 volts. When you turn off, it actually improves the E-off losses by 25%. And that improves your switching losses. So that's a big benefit, some of onsemi's silicon carbide.
So, Bob, we also need to talk about isolation here as well, right?
Yes, isolation's an important piece of the whole puzzle and kind of a rule of thumb for me. And you always want to discuss this with your customers. For low power applications that are below 2.5 kilowatts, you typically don't need isolation between the gate driver and the switch. However, when you get to more higher power applications, like let's just say over 2.5 kilowatt, that's a fuzzy line in the sand. You want to discuss that with your customers. That's where you might want to consider the isolation in the gate driver. So we use this galvanic isolation, which is similar to the isolation of a transformer, using inductors inside of our chips. And what that does is it separates the grounds between the high power section on the right and the low power section on the left. So it improves your signal integrity for keeping the ground loops separated, but it also helps protect the user for safety concerns. So the user's typically touching things, interacting on the low power side. You don't want that high power to accidentally shock the user.
That makes sense. Now, what kind of solutions does onsemi offer when it comes to BLDC HV MOSFET gate drivers?
Yes, onsemi offers a full portfolio of high voltage MOSFET gate drivers for BLDC. And in this plot, so the x-axis captures the gate source and sink drive. So when you turn a switch on, you source current. When you turn it off, you sink the gate driver sinks current from 250 milliamps all the way to 6 amps. And then for the y-axis, that captures the working voltage of these gate drivers, which correlates to the motor voltage. And everything in orange is that 3 half-bridge gate driver. So you'd only need one of those chips to drive one BLDC. Or in gray, we have single half-bridge gate drivers. And so you'd need 3 of those to drive the motor. So we have a full portfolio to meet all your needs for the MOSFETs.
So, what about IGBT solutions? Bob, what does onsemi offer here?
onsemi has a full portfolio. It's a one-stop shop for both switches and gate drivers. We have the single-channel IGBT gate drivers on the top table and some of our dual-channel IGBT gate drivers on the bottom table. For both tables, the first column captures the product numbers. The second column are the key features. The third column, moving left to right, is the package type. The fourth column, moving left to right, is the undervoltage lockout, followed by the propagation delay in nanoseconds, and then finally the availability. And they're all available for ordering.
Excellent. So, what about silicon carbide? What does onsemi offer in this case?
Right. So onsemi is a global leader in silicon carbide. And so what I did in this slide is I paired the gate drivers that from a first order approximation would go with our elite SiC MOSFET. So on the far left, we'll start with the breakdown voltage. So many customers, when they design a brushless DC motor, they start with the switches. They want to get the right switch for the amount of power that they're going to be requiring. And so the breakdown voltages correlates to that power. And so it goes from 650, 750, 900 volts, 1200 volts, 1700 volts. Next column are the RDS on ranges. So when you fully enhance or turn on that switch, the ID current that's flowing through the switch is going to dissipate power, conduction losses. That's going to be driven by your RDS on. The third column is the packaging. It's always important to get your packaging. And then, so the next set of columns, the next 2 columns, is what we recommend for a gate driver for 5 kilovolt RMS galvanic isolation. The first column is the 6.5 amp source, 6.5 amp sink gate drive, followed by the 4 amp source, 6 amp sink gate drives for single. And then for the dual channel, we have the source and sink capability, as well as the total propagation delay matching. So a lower number, that's in nanoseconds. So a lower number is better. That helps prevent shoot through current in a half bridge application. And then down below, we've got a number of different footnotes. Number 1 supports the external negative bias turnoff, which I mentioned earlier, helps on your E-off losses. The number 2 supports the desaturation, which is an overcurrent protection, which is important to a lot of customers. Number 3 is the active Miller clamp protection, which protects the gate to source voltage or clamps it, preventing accidental turn on during intended turn off. And finally, the V supports the automotive qualification.
All right. So, Hunter, we've talked about power trench in a previous Chalk Talk, but that would be a good fit for these kind of applications, right?
You're exactly right, Amelia. So to kind of jump into it to start with the lower voltage part of onsemi's portfolio to fit these industrial drives, and specifically our next generation Power Trench 10 silicon MOSFETs, and sort of the value proposition that comes with these devices. In the semiconductor industry, we're always aiming for higher efficiency, higher power, and better reliability. And what that translates to with T10 devices over our previous generation, like T6 and T8, you see a 30 to 40% reduction in the specific resistance, which directly correlates to the RDS on and your conduction losses. You see a 2 times reduction in various switching parameters like your gate charge or the charge of your internal capacitance of that device. They have softer recovery diode and lower reverse recovery charge, and a 10% higher unclamped inductive switching capability. So for our T10 devices, they're optimized into 2 different categories. We have T10S, which are those optimized for faster switching applications, DC to DC converters typically, whereas T10M, those on the right, are going to be those optimized for motor control, these industrial drives, these variable frequency drives that we'll see, and the switches that we'll adopt into these next generation BLDC motor drives. And then on the right, you can see a table that details all of our existing released T10 devices ranging from 40 volts to 80 volts. In the first column, you have your part number. In the second column, you have your package type. Most of what we have available are SO8FL 5x6s or 5mm by 6mm packages. It's sort of the industry standard. And what you can see here, and something very important to note, is that onsemi is ahead of the curve for developing next generation silicon MOSFETs. At the moment, those highlighted that you can see, we have the lowest RDS(on) in the market. And with continued developments of T10, next generation T12, and so on and so forth, we expect to stay a leader for quite a while.
All right. So, Hunter, what kind of trends are you seeing when it comes to power packages for these kind of designs?
So for power packages specifically related to our silicon MOSFET portfolio, there's a number of things that we're doing to improve the performance of these devices. So first and foremost, in the top left, I'll talk about die metallization. We're seeing the trend moving away from single aluminum to double aluminum layered to now a thick copper layer. And the benefits that we see with this is it reduces lateral and contact resistance, it improves transient thermal impedance, and it enhances reliability due to a higher temperature gate bias and high temperature reverse bias. And that relates to reliability. In the top right, you have the interconnection. This is basically how you connect the pins of the device to the internals of the device. Previously, that was done with wire bonding, aluminum wire bonding, moving now to a copper clip and now a thick copper clip. So the benefits that we see with that are reducing package resistance and inductance. Bottom left, you see improvements that we're making in soldering and the die attach. But previously, just with standard solder, moving to a low alpha solder, and now with silver sintering. Benefits here are enhancing reliability with the high temperature gate bias and reverse bias, reducing the connection resistance, improving the transient thermal impedance, and improving steady state thermal resistance. And then lastly, for the encapsulation of the device, the epoxy, the molding compound that goes into that package, we're moving to a higher thermal conductivity epoxy, which improves the reliability when it comes to delamination of the package when you have thermal cycling, and then the improvement in thermal resistance to the case or to ambient, as you can see with the R theta J parameters that are commonly called out and looked for in data sheets. And then we have a number of devices that are available. Really, what you'll see in the industry from onsemi being included in your designs is anything ranging from really 3x3 packages all the way up to 10x12s. And a number of configurations. Dual cool is hot on the block. Substantial improvements with thermal performance with those devices. Top cool if you're looking to achieve higher power density and reduce the size or the area of your PCB. So really a number of package improvements, as you can see from this.
Okay, so Hunter, what about higher power transistors?
So for the higher power transistors that onsemi has in our portfolio, it really comes down to IGBTs and silicon carbide devices, which Bob gave a fantastic overview of previously. But I'll tell you what we have recently released, sort of the latest of our IGBT portfolio, that best bang for your buck, high performance, good cost devices. It's going to be our 1200 volt field stop 7 devices. So much like our T10 power trench silicon MOSFETs, our field stop 7 IGBTs, and really our entire IGBT portfolio, is separated into a couple different categories. You've got your R series, which is your medium speed devices. These are optimized for lower VCE sat. That's sort of the analog to your RDS(on). If you have lower VCE sat, these perform better with conduction losses and in these motor control designs. Really, your switching frequency is on the order of roughly 20 kilohertz. Depends, it varies, and with a variable frequency drive, it varies that frequency, but that's maybe sort of the middle range that you'll see. And then the fast series devices, these are optimized for higher switching frequency power conversion. You're talking 70 kilohertz, 100 kilohertz, a little bit higher. These devices have an optimized diode for low forward voltage and softness, so an optimized anti-parallel diode. And we do have both the R series and the S series devices released. So you can see in this graph here with these three curves, there's a trade-off between VCE sat and switching losses. And that's why we have two different categories of devices. If you look on the curve on the far left, You've got the little orange dot, the one that's furthest to the left, and then the darker brown dot that's at the very bottom of the curve. So you can see, depending on how we tune the device and tune the specifications of the die, you achieve either a device that's more optimized for motor control applications, again with that low VCE sat, or for switching-based applications with very low switching losses. These FieldStop 7 IGBTs packaged into a number of different configurations, whether in your industry standard TO247 3-lead and 4-lead discretes, into gel-filled power modules, and into some of our intelligent power modules for industrial motor drives. And then you can see for the portfolio that we have available, for what we have released at the moment, the low VC SAT devices they're short circuit rated, they're highly rugged, and they're available in not just the standard 3-lead device, but also in a power TO247 3-lead, where you see the absence of that mounting hole. And that gives you a little bit better thermal performance, and you can package a little bit larger die into it.
Okay, so Hunter, can we also talk about silicon carbide? What kind of benefits would silicon carbide bring here?
Yeah, absolutely. There's a pretty substantial performance benefit over your typical silicon-based devices, and even for motor control applications. And I'll run through a couple of the key material properties for silicon carbide and how they relate to silicon devices. So first and foremost, we talk about the band gap energy. Silicon carbide is a wide band gap material, and what exactly that means is it basically takes more energy for your charges to move from your conduction to the valence band. Basically, all that means is that the device acts a little bit more like an insulator than it does a conductor, and thus you have devices that have a much larger critical electric field. So you can develop much thinner devices. You can see in the bottom left a similar silicon device to a silicon carbide device. Your epitaxial layer is much, much thinner. And you can think about it, the charges are going to flow or conduct vertically through the device. So if your charges have to fight through less material, if that epitaxial layer is thinner, then the resistance of that device is inherently lower. Lower resistance, lower conduction losses, ideal for motor control applications. The next parameter I'll talk about is saturated electron velocity. Basically, what this means is that the charges, when your device is in saturation or fully saturated, move about 2 times faster in silicon carbide based devices versus silicon. They move through the material about 2 times as quickly. And what that results in is much higher current density, and you can reduce the die area quite a bit, and also smaller packages. So if you're increasing the current density, you can reduce the size of that die again, and you can then package those into smaller devices. In an industrial VFD, space constraints, form factor may not be as big of a problem, but what I will say is that for those instances where it may be a bigger issue, maybe on the assembly line, maybe in industrial robotics, where you're really looking to optimize for form factor and size, having smaller packages is a tremendous benefit, and that's really what you see with silicon carbide devices over IGBTs. And then lastly, the thermal conductivity of silicon carbide is about 3 times higher than silicon. So what that means is that you have less complex cooling systems with silicon carbide and faster heat removal. If you would have previously used a water-cooled system, you could now move to natural or forced convection with just a standard heatsink. Or if you had a very large heatsink, you could now move to a slightly smaller heatsink.
All right. So, Hunter, what does onsemi offer in terms of silicon carbide solutions for industrial motor drives?
So you can see our entire Elite SiC portfolio that we recommend for this application here in the table on the left. And this is broken out by part number in the first column, technology, your breakdown voltage, your RDS on, and then your package type. The technology, our M2 and our M1 devices, these are sort of our first generation devices. These have higher short circuit withstand time over our third generation devices. So at the moment, these tend to be recommended for industrial drives. For our third generation devices, we do have 2 devices optimized for industrial drives, and that's our M3P. These are going to have roughly a 2 microsecond short circuit withstand time, which also works well for industrial drives, where really you're going to see about a 1.75 microsecond requirement for the short circuit withstand time for industrial drives. And we have through-hole packages available in TO247 3-lead and 4-lead 4-lead for improved switching losses, and surface mount packages as well, and the D2 Pack 7-lead, the TO leadless, and in the PQFN 8x8.
So, what does onsemi offer in terms of intelligent power modules?
For our intelligent power modules, first, I think it makes most sense to explain a little bit what they are, since we have standard power integrated modules and then those intelligent power modules. So what these devices do is they basically have the integrated gate drivers, those half-bridge gate drivers, so you don't need to worry about factoring them into your layout and your PCB design. It's factored all into one package, both the high side and the low side drivers. You have all 6 of the switches that are required that are integrated into that package as well. They have built-in temperature sensing and protection, things like overcurrent protection, under voltage lockout and shoot-through prevention, and very low thermal resistance substrates. We have aluminum oxide and aluminum nitride DVCs available. We also have a ceramic option for the SPM45 package. Here you can see the power correlated to each one of the packages. As you would assume, as the packages get bigger, you can move to higher power. And as the packages integrate standard silicon MOSFETs and then to high power IGBTs, you also get higher power. So everything ranging from quarter horse or 200 watts with the SPM7 all the way up to 13.4 horsepower and roughly 10 kilowatts for our SPM49 package. And then for the future and things to expect coming out, you could imagine that we'll be integrating Field Stop 7 and silicon carbide into some of our next generation intelligent power modules, which we're already sampling at the moment, the SPM31 and SPM3V. Again, utilizes Field Stop 7 and silicon carbide for roughly 8 kilowatt industrial drives.
All right. So, Hunter, we should also talk about current sensing as well, right? What kind of solutions do you guys offer here?
We're looking to optimize efficiency and improve cost in these systems. So what onsemi offers is very, very low offset voltage current sense amplifiers. So you can see some of the older devices, the LM2904/LM358, roughly 7 millivolts for that offset voltage. Whereas for one of our latest, the NCS21801, 10 microvolts for the offset voltage, much, much lower. And what that means and why that's important is that if you're looking to measure the current in a particular motor drive application, you're usually going to do that through a shunt resistor. And ideally, you'd like to use a smaller resistor, in which case you need a lower offset voltage amplifier in order to be able to measure the difference, the change in the shunt drop across that resistor. So if you reduce the voltage drop across that sensing resistor, you reduce power dissipation and you improve system efficiency. You can measure that shunt drop with a much smaller resistor or lower offset voltage operational amplifier.
All right. Well, I think that's all I have time for today. Thank you so much for joining me, Hunter.
Thank you, Amelia.
And thank you for joining me, Bob.
Thank you very much, Amelia. I appreciate it.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from onsemi. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.